Artificial intelligence, AI. Interaction design is an interdisciplinary field that focuses on shaping how humans interact with intelligent systems in meaningful, usable, ethical, and efficient ways. Unlike traditional human-computer interaction, HCI, AI interaction design must address systems that learn, adapt, predict, and sometimes act autonomously. This creates unique challenges related to transparency, trust, control, accountability, and user understanding. The purpose of this study is to provide a comprehensive analysis of AI interaction design, examining its theoretical foundations, practical methodologies, technical constraints, ethical implications, and future directions. The study adopts an analytical and descriptive approach, offering detailed explanations intended for academic, professional, and applied design contexts. AI interaction design refers to the structured and systematic process of designing interfaces, interaction flows, behaviors, and overall user experiences that enable effective, meaningful, and trustworthy communication between humans and AI-driven systems. Unlike traditional interface design, which primarily focuses on visual elements and fixed interaction patterns, AI interaction design encompasses a much broader scope. It integrates decision-making logic, system feedback mechanisms, learning models, and adaptive behaviors that evolve in response to user input, contextual data, and environmental changes. The primary objective of AI interaction design extends beyond basic usability to include intelligibility, predictability, transparency, and sustained user confidence. Users must not only be able to operate the system efficiently, but also understand how and why the system behaves in certain ways. This understanding is essential for forming accurate mental models of the AI system, reducing confusion, and preventing misuse or over-reliance on automated decisions. A critical aspect of AI interaction design is its need to manage uncertainty. AI systems often produce probabilistic outputs rather than definitive answers, relying on statistical inference and pattern recognition rather than deterministic rules. Designers must therefore create interaction mechanisms that clearly communicate confidence levels, possible errors, and alternative outcomes. This includes designing explanations, warnings, and feedback loops that help users interpret AI-generated results appropriately. Additionally, AI-driven systems are inherently dynamic. Their behavior may change over time as models are retrained, data distributions shift, or user behavior evolves. This continuous adaptation introduces challenges related to consistency, predictability, and long-term user experience. AI interaction design must anticipate these changes and ensure that evolving system behavior does not undermine user trust or usability. As a result, AI interaction design differs fundamentally from static software design, where system behavior is fully predefined and predictable. In static systems, designers can specify every possible interaction in advance. In contrast, AI systems require designers to plan for ambiguity, learning, and autonomy, making AI interaction design a complex discipline that blends design thinking, cognitive science, ethics, and advanced computational understanding. The roots of AI. Interaction design can be traced back to early human-computer interaction, HCI, research conducted during the 1970s and 1980s, a period in which the primary concern was improving usability, efficiency, and ergonomics in computing systems. At that time, computers were largely static, rule-based machines, and interaction design focused on optimizing input methods, screen layouts, command structures, and error prevention. The goal was to reduce physical and cognitive strain on users, ensuring that systems were accessible and functional for trained operators rather than adaptive to individual users. As computing power increased and artificial intelligence research began to mature, particularly in the 1980s and 1990s, interaction models grew significantly more complex. Early AI systems, such as expert systems, attempted to replicate human decision-making through predefined rules and knowledge bases. These systems introduce new interaction challenges, including how to present recommendations, how to justify automated decisions, and how to allow users to intervene or override system logic. Interaction design during this phase began to shift from purely interface-focused concerns towards supporting reasoning, explanation, and trust. The late 1990s and early 2000s marked a major turning point with the rise of machine learning, data-driven models, and natural language processing. Unlike rule-based systems, these technologies enabled systems to learn from data, adapt over time, and operate with a degree of uncertainty. This transformation fundamentally altered the nature of interaction design. Designers were no longer working with fully predictable systems. Instead, they had to account for probabilistic outcomes, evolving behaviors, and personalized responses. Interaction models needed to communicate uncertainty, learning progress, and system limitations in ways that users could understand. The widespread adoption of voice assistants, recommender systems, and conversational agents in the 2000s further accelerated this evolution. Technologies such as virtual assistants, chatbots, and personalized content platforms introduced continuous, context-aware interaction that extended beyond traditional screen-based interfaces. Users began interacting with AI systems through speech, gestures, and ambient interactions, often without explicit commands. This shift required new design paradigms that emphasized natural language interaction, conversational flow, emotional tone, and context sensitivity. Over time, AI interaction design expanded to incorporate insights from cognitive science, behavioral psychology, and human-centered design. Researchers and practitioners recognize that effective interaction with AI systems depends heavily on human perception, decision-making, attention, and emotional response. Concepts such as mental models, trust calibration, cognitive bias, and user motivation became central to the design process. Design thinking methodologies were also adopted to address the ambiguity and complexity of AI-driven systems, emphasizing iterative prototyping, user testing, and interdisciplinary collaboration. Today, AI interaction design represents a convergence of multiple disciplines, shaped by decades of technological advancement and research. It reflects a shift from designing tools that users control directly to designing intelligent partners that collaborate, recommend, and sometimes act autonomously. This historical evolution highlights how interaction design has adapted in response to increasingly intelligent systems, laying the foundation for current and future human AI interaction paradigms. Several fundamental principles serve as the foundation for effective AI interaction design, providing both theoretical guidance and practical strategies for creating systems that are usable, trustworthy, and ethically responsible. One of the most critical principles is transparency. In the context of AI, transparency goes beyond simple visibility of system functions. It involves enabling users to understand the rationale behind system behavior, the sources of its recommendations, and the mechanisms by which decisions are made. Transparent systems reduce confusion, prevent over-reliance, and help users form accurate mental models, which are essential for building trust and facilitating informed decision-making. Transparency can be achieved through techniques such as visual explanations, natural language summaries, confidence indicators, and interactive data visualizations that illustrate the system's reasoning process in an accessible way. Another central principle is feedback, which ensures that users are constantly informed about system status, ongoing processes, and the results of AI-driven actions. Effective feedback allows users to monitor the impact of their inputs, recognize errors early, and adjust their behavior accordingly. In AI systems, feedback must be both immediate and contextually meaningful, particularly because these systems often operate in dynamic, adaptive environments. Feedback mechanisms may include real-time notifications, progress indicators, detailed error messages, or interactive explanations of recommendations. Providing rich feedback is crucial for maintaining user engagement, fostering understanding, and reducing anxiety associated with automated decision-making. User control is another cornerstone of AI interaction design. While AI systems are designed to operate autonomously or semi-autonomously, users must retain the ability to intervene, correct, or override system actions. Control mechanisms empower users, prevent undesirable outcomes, and enhance perceived reliability. Examples include manual overrides, adjustable levels of automation, and interactive decision-making interfaces where users can modify recommendations or refine system behavior. Striking the right balance between automation and control is essential. Excessive automation can lead to user disengagement, while insufficient automation can reduce system efficiency and usefulness. Consistency is equally important, particularly in AI systems where behavior may evolve over time due to learning or adaptation. Consistent interaction patterns, predictable responses, and standardized terminology help users form expectations and reduce cognitive load. Even in adaptive systems, designers must ensure that changes are gradual, well-signaled, and accompanied by explanations to avoid disorienting users. Maintaining consistency across different contexts, platforms, and interaction modes further strengthens usability and trust. In addition to these principles, robustness and error tolerance are critical considerations. AI systems are inherently imperfect due to limitations in data, algorithms, and computational models. Designers must anticipate potential failure cases such as misclassifications, incorrect predictions, or unexpected system behavior, and design interactions that allow users to recover gracefully. Error-tolerant designs may include undue functionality, fallback options, redundant confirmation mechanisms, and clear communication of uncertainty. Communicating uncertainty effectively is particularly important in probabilistic AI systems, as it prevents overconfidence and supports informed decision-making. Furthermore, these principles are interdependent and must be integrated holistically into the design process. Transparency without feedback may leave users informed in principle but confused in practice. Control without robustness may create frustration when interventions fail. Consistency without flexibility may hinder adaptation to diverse user needs. Effective AI interaction design therefore requires careful consideration of the interplay between these principles, iterative testing, and continuous refinement to accommodate both technological constraints and human cognitive, emotional, and behavioral factors. By adhering to these guidelines, designers can create AI systems that are not only functional, but also comprehensible, trustworthy, resilient, and capable of delivering meaningful and satisfying user experiences. Human cognitive limitations play a central and decisive role in AI interaction design, as the effectiveness of any AI-driven system ultimately depends on how well it aligns with human perception, reasoning, and decision-making processes. Unlike machines, humans do not naturally think in probabilities, statistical distributions, or abstract computational models. As a result, users often struggle to interpret probabilistic outcomes, confidence scores, and machine-generated recommendations, especially when these outputs are presented without adequate explanation or contextual support. This gap between machine logic and human cognition represents one of the core challenges of AI interaction design. One of the most important cognitive factors to consider is cognitive load. AI systems can easily overwhelm users by presenting too much information, too many options, or overly complex explanations at once. When cognitive load exceeds a user's processing capacity, comprehension decreases, errors increase, and frustration grows. Designers must therefore prioritize clarity, hierarchy, and progressive disclosure, presenting information in manageable portions and allowing users to access deeper details only when needed. This is particularly important in AI systems that continuously generate insights, predictions, or recommendations. Attention span is another critical limitation. Modern users often interact with AI systems in environments filled with distractions, making sustained attention difficult. If AI interactions require excessive focus or frequent interruptions, users may ignore important feedback or misinterpret system outputs. Designers must carefully time notifications, feedback, and explanations to align with natural attention patterns. ensuring that critical information is delivered when users are most receptive. Memory limitations also significantly affect how users interact with AI systems. Humans have limited working memory and may struggle to remember previous system actions, past recommendations, or the rationale behind earlier decisions. Poor memory support can lead to confusion and inconsistent usage. AI interaction design should therefore include mechanisms such as summaries, history views, reminders, and visual cues that help users recall prior interactions and understand how the system has evolved over time. Another crucial concept is the formation of mental models, which are the internal representations users create to explain how a system works. If an AI system behaves in ways that contradict a user's mental model, trust quickly erodes. Poorly designed AI interactions can cause users to either overestimate the system's capabilities, leading to blind reliance, or underestimate them, resulting in rejection or avoidance. Both extremes are problematic. Designers must actively shape accurate mental models by clearly communicating what the system can do, what it cannot do, and under what conditions it may fail. When AI interactions are poorly designed, the consequences can be significant. Users may experience confusion due to inconsistent behavior, over-reliance due to unexplained automation, or complete distrust when the system makes errors without justification. In high-stakes domains such as healthcare, finance, or security, these outcomes can have serious real-world implications. To address these challenges, designers must align system behavior with human expectations while also educating users about the inherent limitations of AI systems. This involves designing interactions that feel intuitive and familiar, while gradually introducing concepts such as uncertainty, learning, and probabilistic reasoning in accessible ways. By respecting human cognitive constraints and supporting users through clear, empathetic, and informative interactions, AI interaction design can bridge the gap between complex machine intelligence and human understanding, ultimately leading to safer, more effective, and more trusted AI systems. User experience in AI systems is inherently dynamic rather than static because AI-driven applications continuously learn, adapt, and evolve based on data, user behavior, and contextual factors. Unlike traditional software where functionality and interaction patterns remain fixed after deployment, AI systems may change their behavior over time without direct user input. These changes directly influence how users perceive, understand, and trust the system, making user experience design a long-term and ongoing responsibility rather than a one-time design task. As AI systems adapt through learning mechanisms, the user experience can shift gradually or sometimes unexpectedly. Recommendations may become more personalized, system responses may vary, or automated decisions may change as models are updated. While these changes are often intended to improve performance, they can create confusion or discomfort if users are not aware of what is happening. For this reason, continuous evaluation and iteration are essential. Designers must regularly assess real-world usage, analyze user feedback, and refine interaction patterns to ensure that system evolution remains aligned with user expectations and goals. Onboarding plays a critical role in shaping long-term user experience. Effective onboarding introduces users to the system's purpose, capabilities, and limitations in a clear and accessible way. It helps users understand how the AI learns and how their interactions influence system behavior. Without proper onboarding, users may develop unrealistic expectations or misunderstand the system's role, leading to frustration or misuse. Thoughtfully designed onboarding experiences build trust and prepare users for future changes. Long-term usage presents additional challenges as users interact with AI systems over extended periods. Over time, users may forget how certain features work, rely too heavily on automation, or struggle to adapt when the system evolves. User experience design must support sustained engagement by offering reminders, summaries of past interactions, and explanations of behavioral changes. These elements help users maintain a clear understanding of the system and reduce frustration caused by unexpected outcomes. Learning curves must also be carefully managed in AI systems. Advanced AI features can be complex and intimidating, particularly for users with limited technical knowledge. Gradual feature exposure and clear guidance allow users to develop confidence at their own pace. By introducing functionality progressively, designers can prevent cognitive overload and encourage meaningful exploration of the system's capabilities. Changes in system behavior must be communicated clearly and consistently. When AI systems update their models or modify decision logic, users should be informed in a way that preserves predictability and understanding. Consistent interaction patterns and clear explanations help users maintain stable mental models even as the system evolves. By focusing on clarity, continuity, and adaptability, user experience design for AI systems can remain usable, trustworthy, and effective throughout the entire life cycle of the technology. Explainability is a critical component of AI interaction design, especially in high-stakes domains such as healthcare, finance, and governance. Users must be able to understand the rationale behind AI decisions to build trust and make informed choices. Interaction designers collaborate with engineers to translate complex model outputs into human-readable explanations. This may include visualizations, natural language summaries, or confidence indicators. Trust in AI systems is not automatic and cannot be assumed simply because a system appears intelligent or technologically advanced. Instead, trust must be carefully earned and maintained through consistent, reliable, and understandable interactions over time. Users develop trust based on their experiences with the system, how accurately it performs, how transparently it communicates, and how well it supports user goals. When trust is poorly managed, users may either rely on the system too much or reject it entirely, both of which can undermine the effectiveness and safety of AI-driven applications. Overtrust in AI systems can be particularly dangerous. When users blindly follow AI recommendations without questioning or understanding them, they may overlook errors, biases, or context-specific limitations. This is especially problematic in high-stakes environments such as healthcare, finance, security, or transportation, where incorrect decisions can have serious consequences. Overtrust often occurs when AI systems present outputs with high confidence but without sufficient explanation, leading users to assume that the system is always correct. Interaction design must actively prevent this by encouraging appropriate levels of user engagement and critical thinking. Undertrust, on the other hand, can lead users to ignore or avoid AI systems altogether, even when they provide accurate and valuable support. This may occur when systems behave unpredictably, fail without explanation, or do not align with user expectations. In such cases, users may perceive the AI as unreliable or unsafe, reducing adoption and diminishing potential benefits. Effective interaction design seeks to avoid both extremes by calibrating trust rather than maximizing it. Calibrating trust requires clear communication of system confidence levels, limitations, and uncertainty. AI systems often operate using probabilistic models, meaning their outputs are not guaranteed to be correct. Designers must present this uncertainty in ways that users can understand, such as confidence indicators, alternative options, or explanations of contributing factors. By making uncertainty visible rather than hiding it, interaction design supports more informed and responsible decision-making. Transparent and minimal feedback plays a crucial role in building sustainable user confidence. When users receive timely feedback that explains why a recommendation was made or why an outcome occurred, they are more likely to develop realistic expectations of system performance. Over time, repeated positive experiences combined with honest communication during failures help users build a balanced and resilient trust relationship with the AI system. Ultimately, trust in AI systems is a dynamic and ongoing process rather than a fixed state. it evolves as users gain experience, encounter successes and failures, and refine their understanding of the system's capabilities. Interaction design serves as the bridge between complex AI processes and human judgment, shaping how trust is formed, adjusted, and sustained. By prioritizing transparency, consistency, and user empowerment, designers can foster appropriate trust that enhances both user confidence and system effectiveness. AI interaction design carries significant ethical responsibilities because the ways in which users interact with AI systems can directly influence behavior, decisions, opportunities, and outcomes. Design choices are never neutral. The structure of an interface, the framing of recommendations, and the presentation of automated decisions can unintentionally reinforce social biases, marginalize certain user groups, or subtly manipulate user behavior. As AI systems become more embedded in everyday life, the ethical implications of interaction design become increasingly important and far-reaching. One of the most serious ethical concerns is bias. AI systems often learn from historical data that may reflect existing social or institutional inequalities. If interaction design does not acknowledge and address these biases, it can amplify unfair or discriminatory outcomes. The way information is presented, ranked, or emphasized can shape user decisions and limit opportunities for certain groups. Ethical interaction design requires awareness of these risks and the creation of interfaces that allow users to question, understand, and challenge AI-driven outcomes. Inclusivity and accessibility are essential elements of ethical AI interaction design. Systems must be usable by people with different abilities, cultural backgrounds, languages, and levels of technical knowledge. Poorly designed interactions can exclude users with disabilities or reinforce digital inequality. Ethical design practices focus on inclusive design principles, support for assistive technologies, clear language, and flexible interaction methods that accommodate diverse user needs. Respect for user autonomy is another fundamental ethical responsibility. AI systems often guide users through recommendations or automated decisions, which can be helpful but also potentially manipulative. When users are not given meaningful choices or clear explanations, their ability to make independent decisions is reduced. Ethical interaction design ensures that users remain in control by offering options to adjust system behavior, override automated actions, and understand how recommendations are generated. AI interaction design also affects power dynamics between users and organizations. Companies that design and deploy AI systems often control data, algorithms, and outcomes, while users may have limited visibility into how decisions are made. Interaction design can either reinforce this imbalance or help reduce it by increasing transparency and user empowerment. Ethical designers must consider who benefits from the system, who may be harmed, and how interaction choices influence these relationships. Privacy is a critical ethical concern in AI systems. Many AI applications rely on personal data, making it essential to communicate data practices clearly and honestly. Users should understand what data is collected, how it is used, and how it impacts system behavior. Ethical interaction design avoids confusing or deceptive consent mechanisms and prioritizes clarity and user understanding. To address these ethical challenges effectively, ethical frameworks and guidelines must be integrated into the AI interaction design process from the earliest stages of development. Ethics should be a core design consideration throughout research, prototyping, testing, and deployment. By embedding ethical thinking into the design process, AI interaction design can support systems that are not only intelligent and efficient, but also fair, respectful, and aligned with human values. AI systems rely heavily on user data to function effectively, making privacy a central and unavoidable concern in AI interaction design. The ways in which data is collected, processed, and stored have a direct impact on user trust and acceptance of AI systems. Interaction design plays a critical role in communicating these data practices to users in a clear and understandable manner, ensuring that users are aware of how their information is being used and what level of control they have over it. Well-designed interaction patterns such as consent mechanisms, privacy dashboards, and clear data explanations help users make informed choices about their data. Consent should be meaningful rather than hidden behind complex language or confusing interfaces. Privacy dashboards can provide users with an overview of what data is collected and allow them to manage preferences easily. Clear explanations of data usage help reduce uncertainty and build confidence in the system. Poorly designed privacy interactions can quickly lead to mistrust, user frustration, and even legal or regulatory non-compliance. When users feel that data practices are unclear or misleading, they may disengage from the system or reject it entirely. For this reason, transparency is essential, but it must be carefully balanced with simplicity. Overloading users with technical details can be just as harmful as providing too little information. Effective AI interaction design presents privacy information in a simple, accessible way, while still respecting the user's right to understand and control their data. Evaluating AI interaction design requires a comprehensive approach that combines both qualitative and quantitative research methods in order to capture the complexity and evolving nature of AI-driven systems. Traditional usability evaluation techniques remain important, but they are no longer sufficient on their own because AI systems adapt, learn, and change behavior over time. Evaluation methods must account for both immediate user interactions and long-term user experiences. Qualitative methods play a crucial role in understanding how users perceive and interpret AI systems. Techniques such as user interviews, contextual inquiries, think-aloud protocols, and observational studies help uncover user expectations, mental models, and emotional responses. These methods are particularly valuable for identifying issues related to trust, transparency, and perceived control, which are difficult to measure using numerical data alone. Qualitative insights also help designers understand why users behave in certain ways when interacting with AI-driven features. Quantitative methods complement qualitative research by providing measurable and comparable data. Traditional usability testing can be used to assess task completion rates, time on task, and error frequency. In AI systems, these methods are often extended through longitudinal studies that track user behavior over extended periods of time. Longitudinal evaluation is especially important because AI performance and user perception may change as the system learns and adapts. Additional evaluation techniques such as A/B testing and behavioral analytics are commonly used to compare different interaction designs and measure their impact on user behavior. These methods allow designers to test variations in explanations, feedback mechanisms, or recommendation presentation, and assess which approaches lead to better outcomes. Behavioral analytics can reveal patterns in user engagement, reliance on AI recommendations, and recovery from system errors. Key evaluation metrics in AI interaction design may include task success rates, user satisfaction, perceived trust, confidence in system outputs, and effectiveness of error recovery. Unlike static software, AI systems require continuous evaluation because the behavior may change as models are updated or new data is introduced. Ongoing monitoring and iterative refinement ensure that interaction design remains aligned with user needs and expectations over time. Continuous evaluation is therefore essential for maintaining usability, trust, and overall system effectiveness in AI-driven environments. AI interaction design faces a wide range of challenges that arise from both the technical nature of artificial intelligence and the limitations of human understanding. One of the most significant challenges is unpredictable system behavior. Because many AI systems rely on machine learning models that adapt over time, their outputs may change in ways that are not immediately apparent to users or even to designers. This unpredictability makes it difficult to design interaction that remain consistent and understandable, and it can lead to confusion or loss of trust when system behavior does not match user expectations. Data bias represents another major challenge in AI interaction design. AI systems learn from data that may contain historical, cultural, or structural biases, which can influence system outputs and user experiences. Even when designers aim to create fair and neutral interactions, biased data can lead to unfair recommendations or decisions. Interaction designers must therefore work closely with technical teams to identify potential bias and design interfaces that allow users to recognize, question, and respond to biased outcomes. Technical constraints also limit what interaction designers can achieve. Designers often have little direct control over underlying algorithms, model architectures, or training data. This can restrict the level of transparency or explainability that can be realistically provided to users. As a result, close collaboration with data scientists, engineers, and product teams becomes essential. Effective AI interaction design depends on interdisciplinary cooperation to align technical capabilities with user needs and design goals. User misunderstanding is another persistent challenge. Many users have limited knowledge of how AI systems work and may hold unrealistic assumptions about their intelligence or accuracy. This can lead to over-reliance, misuse, or rejection of AI systems. Designers must find ways to educate users without overwhelming them, helping them develop accurate mental models while maintaining a smooth and intuitive experience. One of the most difficult challenges is communicating uncertainty without reducing usability. AI systems often produce probabilistic outputs rather than definitive answers, but presenting uncertainty can make interfaces feel complex or less reliable. Designers must balance honesty and clarity with simplicity and confidence. Poor communication of uncertainty can either erode trust or create false confidence. Addressing this challenge requires careful design of explanations, feedback, and visual cues that support informed decision-making while preserving a positive user experience. Future developments in AI interaction design are expected to significantly expand the ways in which humans engage with intelligent systems, introducing new opportunities as well as complex challenges. One of the most important trends is the growth of multimodal interaction. AI systems are increasingly capable of processing and responding to multiple input and output modes, such as text, voice, gesture, facial expression, and visual context. This shift allows interactions to feel more natural and fluid, but it also increases design complexity. Designers must ensure that different interaction modes are well coordinated, consistent, and accessible so that users can move seamlessly between them without confusion or loss of control. Another major development is the rise of emotion-aware systems. Advances in affective computing enable AI systems to detect and respond to emotional cues, such as tone of voice, facial expressions, or behavioral patterns. While this has the potential to create more empathetic and supportive user experiences, It also raises significant ethical and design challenges. Designers must carefully consider accuracy, privacy, and consent, as well as the risks of misinterpretation. Interaction design will need to balance emotional responsiveness with transparency and user comfort, ensuring that emotion-aware features enhance rather than undermine trust. Adaptive personalization is also expected to become more sophisticated. Future AI systems will increasingly tailor content, recommendations, and interaction styles to individual users in real time. While personalization can improve relevance and efficiency, it can also make system behavior less predictable. Designers must ensure that personalization does not isolate users, reinforce bias, or reduce user autonomy. Providing users with visibility and control over personalization settings will be essential for maintaining trust and understanding. In parallel, increased regulatory oversight is likely to shape the future of AI interaction design. Governments and institutions are developing regulations related to data protection, transparency, accountability, and ethical AI use. Designers will need to incorporate regulatory requirements directly into interaction design, ensuring that systems clearly communicate rights, responsibilities, and limitations. Compliance will no longer be only a legal concern, but a core design challenge. As AI systems become more autonomous, interaction designers will face the task of preserving human agency while allowing systems to act independently. Designers must define clear boundaries between human and machine decision-making and create interactions that support collaboration rather than replacement. Advances in explainable AI and human-centered AI research are expected to play a critical role in shaping these new interaction paradigms, enabling users to understand, trust, and effectively work with increasingly intelligent and autonomous systems. AI interaction design is a complex and continuously evolving discipline that brings together technology, design, psychology, ethics, and human-centered thinking. It operates at the intersection of advanced computational systems and human experience, focusing on how people understand, use, and relate to intelligent technologies. As AI systems grow more capable and autonomous, interaction design becomes essential for translating complex machine behavior into experiences that humans can comprehend and trust. Effective AI interaction design ensures that systems are not only technically functional, but also understandable and meaningful to users. Functionality alone is not sufficient when systems make predictions, recommendations, or decisions that affect human lives. Users need to understand how AI systems operate, what their limitations are, and how their outputs should be interpreted. Clear interaction design supports accurate mental models, reduces confusion, and prevents both blind reliance and unnecessary skepticism. Trust is another central outcome of well-designed AI interactions. Trust does not emerge simply from high performance or advanced algorithms, but from consistent, transparent, and respectful communication between the system and the user. Interaction design shapes how confidence, uncertainty, and feedback are presented, allowing users to develop realistic expectations of system capabilities. Over time, this balanced trust enables more effective collaboration between humans and AI systems. Alignment with human values is also a defining goal of AI interaction design. Design choices influence fairness, accessibility, autonomy, and ethical responsibility. By considering psychological and social factors, designers can ensure that AI systems support human dignity, inclusivity, and well-being rather than undermining them. Ethical considerations must be embedded into the design process to prevent harm and promote responsible use. As AI continues to integrate into everyday life across domains such as healthcare, education, finance, and communication, the importance of interaction design will only increase. AI systems will increasingly shape how decisions are made and how information is accessed. In this context, AI interaction design plays a critical role in shaping responsible and meaningful human-AI relationships, ensuring that technological progress remains centered on human needs, understanding, and values.